Let's look at this problem which asks us to find the magnetic field everywhere of a coaxial cable. It's got an inner portion which carries current out of the page. I've shaded that with a little pink color. And that current density is not uniform. It's given by A times r to the power 1/2, where A is a positive constant. And that is surrounded by a very thin insulating membrane, the purpose of which is to keep the two currents from mixing. Surrounding that membrane of zero thickness is a sheath also of width A, so that means the distance from the center of the outer edge of the sheath is 2A. And that has got a constant current density J0. Determine the relationship between A and J0 if the magnetic field outside the coaxial cable is 0. Also find where B is maximum and plot it. So typical Ampere's law problem, first of all, if this is coming out of the page, then this current must be going into the page, otherwise you cannot have a net enclosed current equal to 0, which is required for the magnetic field to be 0. So let's quickly run over Ampere's law for this type of symmetry. The only contribution on any of these Ampere loops C sub I I've indicated, C1, C2 or C3, is going to be from the tangential component of the B field. And since the B field as well as the dr vector point in the same direction, I'm going to write that as bt dr cosine 0 degrees. Now, because of the symmetry of the situation, bt cannot depend on anything but the radius, so I can take that out, because this integral is only dependent on the angular coordinate theta. And then when I perform this integral, I'm basically going around the circle, summing up all the magnitudes of the dr vectors. Dr is tangent to the circle. So I'm just going to get 2 pi r. So that's the left-hand side of Ampere law. The right-hand side is given by the various currents enclosed. So first of all, let's answer the first part of the problem. What should be the relationship between these constants A and J0 so that there's no enclosed current at all? So for loop C3, the enclosed current I3 is given by the integral from 0 to A of the first current density times the area element in cylindrical coordinates, and that's going to be 2 pi r dr. And then from A to 2A, you have a constant density J0 times the same area element, 2 pi r dr. So let's try to solve this. We need to set this equal to 0 because the net enclosed current has to be 0 for the magnetic field to be 0 outside. 2 pi cancels out on both sides. So I have A I can take out, integral 0 to A, r to the power 1/2 plus 1, 3/2 dr. And here I can take out a J0. And then I have A to 2A, r dr must be equal to 0. That's A times r to the 3/2 plus 1 divided by 3/2 plus 1 by the rules of calculus. That's going to be r to the 1 plus 1 over 1 plus 1. This can be solved. So I have A times 2/5 A to the 5/2 plus J0 over 2, 2A squared, which is going to be 4A squared minus A squared, is equal to 0. Now you observe that A squared can be cancelled out on both sides, so I'm going to get 2/5 A square root of A, which is left over after you take out A squared from 5 over 5 halves is 2.5. So if you take out 2, you get 0.5, which is a square root. Plus 4a squared minus a squared is 3a squared, and that a squared is no longer there. So I have 3 halves j naught equal to 0. And that is a relationship between a and j naught. You have to have either a equals negative 3 halves j naught over 2/5, or j naught equals, so let me write it in terms of everything in terms of a. So j naught equal to negative 4/15 a root a. So that's the relationship between the two constants for zero magnetic field outside. Observe that if a is positive, then j naught is negative, as it has to be for the total current to be 0. Now, as far as the magnetic field is concerned, it's going to accumulate as you go out in the loop C1, and then it's going to start deaccumulating or decreasing as you go to loop C2. Well, the exact trends are determined by actually solving the problem. So let's do that part next. The left-hand side of Ampere's law remains the same. So for loop C1, I'm going to get Bt times 2 pi r. And here I only have to go from 0 to r instead of from 0 to a. So all I have to do is not write the upper limit as a, but rather write it as r. So I'll stop at this stage and simply take the answer from here. So it's going to be mu naught times that current enclosed. So that's going to be 2/5 a r to the 5 halves. And then if I cancel out a r factor from both sides, I'm going to get 3 halves here. I can take out that 2. So I get Bt must be equal to mu naught a over 5 pi r to the 3 halves. Let me call that Bt1 because it pertains to the Amperean loop C1. The next thing we need to do is do C2. C2 is going to be complicated because now the entire current, the pink stuff, is going to be enclosed, plus whatever is there of the blue up to the loop C2. So what I'll do here is I'll take that entire calculation here, but this calculation I'll go from a to r instead of a to 2a. So almost everything is already here. I just have to copy this part from here because I need the full pink material. And here all I have to do is take r squared instead of 2a whole squared. So that part can be imported. So I just have mu naught 2/5 a to the 5 halves plus j naught over 2. I'll substitute for j naught after this. R squared minus a squared. So that's the expression. And like I promised, I'll eliminate j naught altogether by using what j naught is from that first calculation. So I get mu naught times 2/5 a to the 5 halves minus 4/15 times 2. So that's going to be 2/15 a. I'll write it as a to the half for symmetry times r squared minus a squared. So you can see there's some kind of simplification already because I have a to the 5 halves when I multiply a to the halves and a to the a squared. So that minus becomes a plus. So I'm going to get 2/15 plus 2/5. 2/5 can be written as 6/15. So 6/15 plus 2/15 is 8/15. So I can write this as mu naught 8/15 a to the 5 halves. And then I'm just left with something depending on r. So that's going to be 2/15 a to the half r squared. let me just simplify this a little more. I'll take whatever I can outside. So mu naught, I can take a 2 outside. I can take a 15 outside. Capital A can be taken outside. A square root of A can also be taken outside. Then I have left over inside 4 times, because 4 times 2 is 8, 4 times A squared minus, now I've taken a 2 out, I've taken a 15 out, I've taken a A out, I've taken square root of A out, so I'm only left with an R squared, and that looks very pretty because I know that they have to have the right dimensions, and 4A squared minus R squared has got a good meter squared dimension. Now I'll just divide both sides by 2 pi r, so that tells me that BT in region 2 must be, when I divide by 2 pi r, the 2's cancel out, the pi comes downstairs, so it's going to be mu naught A over 15 pi square root of A times 4A squared over R minus R. So it's going to be a slightly sublinear behavior there. Let's just verify, and I'm keeping my fingers crossed here, that at little r equals A, the two expressions must agree. Is that the case? You can't have weird behavior with Ampere's law. So let's make sure that is true. At r equals A, I'm going to get, this expression is easier to work with first, so I'm going to get 4A squared over A, which is going to be 4A, minus A, which is 3A, and 3A when divided by 15 gives me A divided by 5, and that's exactly what you have here, 5, and then that A that's left over combines with the square root of A to give me A to the 3/2. So the two expressions do agree in that intermediate zone, r equals A. And for r bigger than 2A, this is 0. That's how we got this condition. Let's plot this. That's the last step. And that way you can also figure out where it would be the maximum. The one way to do the maximum is to do calculus on both of them, but it's probably just easier to plot it and see if there's something simple that comes out. So from 0 to A, it's going to be 1.5. 1.5 is a little bit less steep than a parabola. So we can draw a curve that looks like a parabola, I guess, because there's no way to tell. All right. Now from there onwards, it is going to decrease, as if I did not have this term, that would be a strict negative r, which means it's got a slope of -1 time. Actually, it's got a slope of all this, but essentially -1. So it would have gone down like that had there been no term like that. But this is a slightly positive effect. It starts out being slightly positive, which means that you need a value that's slightly bigger than this. So I'll draw something like that. Okay, but in either case, you will notice that the maximum value is achieved at the value A, and that's going to be BT at A. And that maximum value can be simply found by putting A in either of those two expressions. So let's do it here, it's easier there. So it's mu naught A, this is a maximum value, mu naught A to the 3/2 divided by 5 pi, and the maximum value occurs at r equals A. So in this way, and outside, I forgot to plot the outside. Outside it goes to 0. And I also like to sometimes write the ranges in which the Ampere law that rules each kingdom. So that's C1, that's C2, that's C3. Okay, so that's we have completed the problem completely, and found also the maximum value of the magnetic field is exactly in the interface between the two types of currents.